Good afternoon, sir. Our topic name is simulation and analysis of multipath feeding using MATLAB. And group member are Anshuman Singh and myself. And whenever a particular transmitter and receiver wants to send a particular signal to the particular receiver antenna, it will send that particular signal to either of the atmospheric layer, normally ionosphere. What it did, as it will send signal to one of those atmospheric layer and gets reflected towards the receiver. This is the basic thing how communication will occur. But there is the problem if something happens to this sending and reflected signal, then the sended signal which is sent to the receiver is completely lost, and hence it would never be received at receiver. So what happens is that the same signal is sent by the multipath. So like through multipath signal reaches to the receiver and the receiver side, it will take the vector sum of all these different paths and it deduces the information sent that is actually sent by receiver. But in such kind of scenarios, certain random fluctuations or random variations in the amplitude or in the phases observed at the receiver has been found. This fluctuations or random variation is referred as fading. To reduce the effect of fading, error forward correction method is applied, and here we will discuss about relay and Gaussian also. So moving to introduction part. So in mobile communication system, the RF signal propagates from the transmitter to the receiver via multiple different paths due to multipaths. And multipath propagation is usually described by line of sight, that is LOS, and non-line of sight, that is NLOS. You can see in the figure. So when the mobile unit is considerably far from the base station and the LOS signal path does not exist, and the reception occurs mainly from the indirect signal paths. These multipaths have different propagation lengths and thus will cause amplitude and phase fluctuation and time delay in the received signal. Therefore, the main effect of multipath propagation can be described in the terms of fading and delay spread. So next, small scale fading is also called relay fading because if the multiple reflective paths are large in number and there is no line of sight signal component, the envelope of the received signal is statistically described by relay distribution. When there is a dominant non-fading signal component present, such as a line of sight propagation path, the small scale fading envelope is described by Gaussian distribution and thus it is referred to as Gaussian fading. Flat fading is a form of multipath fading which affects all the frequencies across a given channel either equally or almost equally. When flat multipath fading is experienced, the signal will just change in the amplitude and rising and falling over a period of time or with the movement from one position to another position. So that's all about the introduction part, and we already discussed about all these things, what is relay fading and modeling of relay fading. So now we will moving to the simulation part, and it will it will describe by Anshuman.
So now sir, we are going to see about the video demo and stimulation of our coding part. So as mentioned, we are going for a railing and a Recian, so these two fading. So first code is for our railing distribution. So what we are going to do is so first this is my algorithm. So we have to initialize some values and then we have to calculate the in phase and the quadrature component of a railing fading, and then we have to get out of the loop how many times we want to initialize our loop. So the looping depend upon the number of line of sight path, and then after we just have to plot the values. We are taking a GSM frequency of 900 megahertz and the velocity is 100 and number of anomalous path is 20. So this is our code. So I will explain the code in the MATLAB itself. So like sir, this is my MATLAB window. So first of all we have to do CLC clear all close R. So we have to initialize some certain value. So This is first we have to give the GSM frequency, velocity, the c is speed of light, which is 3 into 10 to the power 8. Doppler shift is FD is equal to V by C into FC. Number of line of sight is 20. Initial time is 0. Time step is dt, which is 10 to the power minus 9. Time final is 100 into 10 to the power 9. This time initial, time final, time step is to calculate the number of samples between time initial and time final, and our current time is Ti. So now coming to the calculation of distribution part. So first we have to initialize for loop from k is equal to 1 to number of line of sight that we are going to choose. So if our for calculating for a stationary object, the in phase and the quadrature phase component is 0, and to calculate the railing distribution, first we have to calculate the in phase as well as the quadrature component of the railing fading. So first of all we have to initialize for loop from I is equal to 1 ratio n. This first line is ai is equal to random function. So random function will give you fdt is equal to fd cos ai. So as we know, if we use the vector concept of physics, in physics we will do the in phase and the quadrature phase component of any vector. So we will using here the quadrature phase component cos, because of it will follow the line of sight. So fdt is equal to fd cos theta. Cos theta is what? Ai. And phi is our uni friend from 0 to 2 pi. This is for our range of pi. From 0 to 2 pi the value will be oscillating. So next thing is x is equal to x plus ai cos 2 pi fdt plus phi, which is our in phase component. Y is what? Y plus ai sin 2 pi fct, which is our quadrature phase component, and which is the total end of the loop. After that we have to use rk command, use x and y value to calculate the distribution. So to get the complete distribution of in phase as well as quadrature, this is the expression cos 2 pi f naught tx minus sin 2 pi f naught into y. F naught is what? GSM frequency or input frequency we can say, or carrier frequency we can say. This x and y is what? X and y is our in phase and quadrature phase component values. After that, if you want to plot the envelope, use the formula under root x square plus y square, and end of the loop. And to minimize the railing fading effect, we are going to use the error forward detection method, which is a very efficient and very less expensive in reducing the fadings. So what we are going to do here is the for loop we have to initialize for the stationary object, as well as we have to initialize the for loop for the moving object. So here what we are going to use, for is equal to I is equal to 1 to n, ai is equal to random function, fd is equal to fd cos ai, phi range is from 0 to 2 pi, and after that we have to use a in phase and a quadrature phase component. So what we are going to do is, we are, instead of sending a full information, we are going to send the half of the information, and after that we will send another half of the information, and at the receiver side we will take the vector sum of all the information to get the complete information of this input signal. And as we are initializing a for loop 20 times, that is n times, but we have taken the number of line of sight as 20. So this for loop will give the all information about the number of line of sight of 20, and after that to check the use x and y value to calculate the distribution value. So now our next function f of k will become twice of, as we are getting 0.5, but at the receiver side we have to take the summation. So twice of cos 2 pi f naught t plus into x. This x is our error forwarded detected method at in phase component. This y is what? Quadrature component of the equalizer or the thing of quadrature component. And after that this is our envelope, and then our loop will get out. And now just we are going to plot. So first of all we have to use a time vector to specify our time axis. After that we are using a subplot. So t comma r, time is what? Time axis, r is what? Rayleigh signal. And the title is what? Railing fading before applying error forward detection method, X label, Y label, and this is my velocity. So depending upon the velocity, our fading will occur. If more velocity is there, more Doppler shift will be there, and railing fading or fading will occur more. Similarly, we are doing for a plot figure T comma F. F is what? Fading after applying the error correction method. So if I just run the code, MATLAB is little bit slow. So if I just so if I show you in the PPT itself, so sir, you can see V is equal to 100 meter per second, railing fading before applying. So we can see the maximum amplitude is 4, 3 point something like that, and fluctuation in amplitude is very high. But in the after applying the error forward detection method, you can see the amplitude will get in less than 1. So this is the method of error forward detection method. Now the window will come. So here you can see, sir, maximum value is getting 4.5, 3.5, something like that for V is equal to 100. The same data is used after applying the error forward detection method. You can see the value of amplitude or peak amplitude is getting less than 1. This is showing that our fading effect has been reduced and information loss is not there. This is similarly in the similar manner the code has been written for the Rayleigh distribution also. Here just we have to add one k factor, which is called the Rayleigh factor. K factor, that means in the Rayleigh there is a one concept called line of sight. This line of sight will you can say if you remove this line of sight, the Rayleigh fading is automatically converted into railing fading. So this just in the formula we just have to add the k factor, that is the Rayleigh factor, and the rest code are the same one. Just you have to write the expression in the form of MATLAB, that's it. And if you just run this code, now it's running. So we will see how error forward correction is there in the railing Rayleigh fading. Yeah, it will come. Just a minute. Yeah. So in the PPT I can show you, just a minute. Yeah, it come. So like you can see, sir, here the more fluctuation of the signal is there, first point. Second point is peak amplitude is maximum getting more than 6 something values they are coming before applying the Rayleigh fading, before applying the error forward correction method in it. But in the figure 2 you can see, sir, the fluctuation is very less and we are getting some continuous graph, and our maximum amplitude is 4.2, after that 3.2, and all those things we are getting. In compare with the railing fading giving the far better result compared to the Rayleigh fading, as it doesn't have a line of sight, and it will give the better result compared to the Rayleigh fading. So coming to the PPT, so here we can see, sir, this is code for the Rayleigh fading. We can see maximum we are getting the 6 amplitude, and after the applying we are getting something like that. So the our flat fading has been getting reduced. Along with that, sir, we have done for the dispersion also. So just a minute, I will show you the dispersion part. So along with the fading, dispersion is also the major factor occurring in the wireless communication. So you can clearly see, sir, we are giving the 4 random input signal which is the same amplitude, but we are getting the 4 different type of dispersion. Like in the first figure we can see the signal is narrowing. Signal is broadening in the first figure. You can see signal is getting distorted in the second signal. The amplitude is automatically getting increase in the third one. You can see the signal is getting different like signal bending, signal narrowing, signal broadening. All this thing will occur, that is signal dispersion will occur in our wireless communication as well. Also, sir, we have done this comparison between the channel impulse response for rural and as well as urban area. So like we can see, sir, delay spread, we are calculating the delay spread. So compared to rural and urban area, we can see in the rural area for a short period of a time all my data will get sent, but in urban area it is taking a long time, and we can see like a signal distortion is more in urban area as compared to rural area. So this plot is the impulse response. So as we know, like if we want to check the signal strength, we should plot the impulse response of a signal. So here what we are going to do is we are plotting a rural area and urban area. So for a short time signal is getting sent here, but in the urban area signal take a long time to send. This is the comparison of channel impulse response for rural as well as urban area. And sir, also we have done you can see we have plotted the railing graph, signal amplitude versus time, signal power versus time graph for a stationary object. This is for a stationary object, v is equal to 0. This is for v is equal to 10, v is equal to 10, 100. So as we can see, if we increase the velocity, the Doppler effect will be the more, and automatically the signal amplitude change and fluctuation also increases randomly. And this is my result analysis of Rician fading. If we increase the k loss factor, that is k factor, automatically my fluctuation and amplitude will automatically get increased. And this is I have already explained. And after that, error correction method we have done. And coming to the overall part that we have done for a we have done a simulation and analysis of a multipath fading, and we have covered all the Rician and railing fading, how it get plotted. We have covered the comparison between the impulse responses of urban and the rural area. And sir, also we have compared the signal dispersion which is occurring in the signal wireless communication. So we have discussed the basic problem and a solution of the multiple path fading. Thank you so much, sir.